Hello, everybody. Thank you for coming. Thank you for coming to our first. So just so you know, the reason I have the mic like this and you can't hear it is that it's webcasting, so they'll hear it in the other schools. Unfortunately, here it's not grabbing it. Okay, but thank you again for coming and welcome to our first CITRIS Big Data Seminar Series. I'm Rosalina Aranda, and many of you have emailed me and letting me know that you have come. Thank you so much for coming. Just one announcement. Next month we'll have another series or seminar, and it will be on October 21st. I'll send out an announcement, and you guys are welcome to come to that one as well. Okay? I'm going to pass it over to Dr. Rusu, who will then introduce our guest speaker.
Okay, thank you. So, as Rosalina said, this is the first seminar in a series on big data that CITRIS is running at University of California, Merced. And our first guest is Professor Jeffrey Ullman from Stanford University, who I would say doesn't need any kind of introduction, because if you study computer science, you definitely will study one of his many textbooks on databases. I would say is here. Computational theory, automata, data structures, compilers, and so on. Okay, so today Dr. Ullman will talk about his work on big data, MapReduce, the topic of the day, I would say. So let's invite Dr. Ullman.
Okay, I should be mic'd up now for the, yes? Okay, you want, yeah, okay.
And then just basically with that, this one will make it go forward.
Wait, this? Yeah. This, not that? Yeah. Okay. Okay, anyway, thank you very much for coming here. Anyway, I want to talk about some work that I've been doing over the actually past couple of years. It all has to do with the MapReduce computing system. And I'm going to start, I don't know how many of you know MapReduce. Show of hands. Some. Okay. I'm going to teach you how it works, and in particular, I'll use as an example computing the join of two relations. So I hope that everybody will sort of get an appreciation for what MapReduce is. And then I want to talk about an algorithm design problem using MapReduce, and something that you shouldn't do and how to fix it. And then I want to start giving you the theory that we've been developing for MapReduce algorithms. When I'm feeling manic, I like to think of what we have as the proof that it takes n log n time to sort. Okay, it's just a basic but very natural example of a non-trivial computational complexity result. And then I'll talk about some specific problems and the design of MapReduce algorithms for a couple of common specific problems. So let's see if this works. And it does not. That works. Okay. Anyway, these are my collaborators. Thanks to them. So let's start off by talking about how the MapReduce system works. Now, just to set the stage, and if you're not familiar with it, it's a system for writing parallel programs very easily. In particular, you write parallel programs that are designed to run on large racks of commodity hardware. Okay, this and I'm not going to go into it, but one of the important things that MapReduce or its open source equivalent Hadoop gives you is that when something breaks while you're running your job, and sometimes these jobs are running for hours and hours, something breaks, you don't have to start the job over again. It has this built-in recovery. I'm not actually going to talk about it, but it's a very important aspect of the game. Anyway, to run a MapReduce job, you write two functions. typically Java. The map function, and that takes inputs. We assume the inputs are a very large file of elements of some type. They could be tuples of a relation, documents, web pages, so on. But it's just the input is a large file. Inputs are small elements, all of the same type. And the map function takes an input and produces some number of key value pairs. Could be 0, could be 1, could be 1,000,000. Now, in this sense, keys are not unique, in that the same key can be generated by many from many different inputs. You can even generate the same key from the same input several times if you want. Now, behind the scenes, the key value pairs are sorted by key, and for each key, there's one what's called reducer that gets that key and all its associated values. So the second thing you have to write is a reduce function, and the reduce function takes a key and the list of all its associated values. That's the type of its input, and it produces outputs from that. Okay, and the outputs produced by all the reducers is the output of the whole MapReduce job. Now, you generally divide the work into map tasks and reduce tasks. So a map task will apply the map function to a large number of inputs, typically 64 megabytes worth of input. Reduce tasks, again, typically apply the reduce function to many key list of values pairs. And so that's the unit of parallelism. That is, each task is scheduled at one processor. If you want hardware parallelism, you have to have at least 100 map tasks and 100 reduce tasks. Usually you want to have a lot more than that. Now, this is sort of my own terminology, but I like to think of a mapper as the application of the map function to a single input. And similarly, a reducer is the application of the reduce function to a single key and its list of associated values. Okay, so now I want to work out an example called the natural join. Again, I hope most people are familiar with the idea of a join. So I have two relations, R with columns A and B, S with columns B and C, and what I want to do is find those tuples of R and a pair of a tuple of R and a tuple of S that agree on their B values. And anytime I find a pair, I join them by creating a triple which has the A value from R, the common B value, and the C value from S. Okay. Now the strategy, which by the way was known long before it was MapReduce, it's called sometimes a parallel hash join, is I want to sort of sort everything by the B value. So what I'm going to do is I'm going to use B as the key. Okay. A mapper applied to a tuple R of AB is going to generate the key, which is the B value, and the associated value is actually some notation that says I came from relation R, and my A value is whatever it is. And similarly, if a tuple comes from S, the key will again be the B value, and the associated value will be I came from S, and the C value is whatever it is. So here are a couple of examples. Again, if the mapper gets as input the tuple R of 1, 2, then it produces key 2, and output is R and 1. I came from R, and the other component is 1. Similarly, S of 2, 3, key is 2. Again, that now comes from S. It comes from the first component, is the key. And the value is I came from S, and the other component is 3. Okay, everybody with me so far? Good. Okay, so here's sort of a picture now. In parallel, the mappers are going to be applied to various tuples from the various from the two relations R and S. So this, as I described, R of 1, 2 yields, well, in this case, only one. By the way, in join, the mappers only produce one key-value pair per input. In general, again, it could be 0, 1, any number. Anyway, so there I get, as I said before, 2 and R1 as the value. Here are a couple more examples. In each case, the B value becomes the key, and the associated value is tell which relation did I come from and what was the other component. Okay. Now, behind the scenes, you don't write this as a user. Okay, Hadoop is going to take all the outputs from all the map tasks, the mappers, and sort them by key. Okay, and then there'll be a reducer for each key that appears at least once, and associated with that key will be all the values that all the mappers have produced with that key. So here's an example again. These are the mappers are produced. In this case, each produces one tuple, and boom, they are sent behind the scenes to the reducer for their key. So the three key value pairs that have 2 as the key wind up at the reducer for 2. The one key value pair with key 5 winds up at the reducer for 5. And in this very simple example, there are no other reducers. Okay. Now, small matter is that the system actually doesn't just throw a bunch of key value pairs at a reducer. Rather, it organizes it. Key appears once, and then associated will be a list of all the values that are associated with that key. So here's what the two reducers actually get to see. Okay, key is 2, and then there's a list R1, R4, and S3. Okay, now what does the reduce function do? Okay, now, and so far I've been talking about mechanics of MapReduce. Now I actually have to write a particular reduce function. So again, think of the reduce function applied to a particular key B and some number of values. Some values come from R, some values come from S. And if you think about it, all the values from R that have B value B are going to pair with all of the S tuples that have that same B value. So you're going to get the product of the number of R values from R and the number of values of S. And what you generate, of course, will be, for each pairing, you'll get the A value from R, that's AI, and then B, it's the same, the key value, the key B, always appearing in the middle, and then the third will be whatever the S value, the value from S is. Okay. So again, in this example, for the first case, R1 pairs with S3 to give you 1, 2, 3. R4 pairs with S3 to give you 4, 2, 3. For the key 5, you don't get anything out because there are no R values. Okay? Okay, now I want to talk about a particular problem that came up. Last year, every year we teach a big data project course at Stanford. And I coach some of the teams and some of the other faculty coach teams. And one of my teams had data from the Stanford, the medical school, where they had actually transcribed 20 years worth of handwritten doctor's notes, digitized them. Okay. My guys had already, as part of their work in the med school, had extracted records about certain drugs. about really all the drugs. There are only surprised me, there are only 6,000 different drugs that are legally administered in this country. Anyway, I want to emphasize that these guys actually did a wonderful job. They were looking for interactions of drugs that caused heart attacks. And once they got it right, they were able to identify from their data about half of the 80 pairs of drugs that are known to cause heart attack. And they also discovered 2 other pairs that were not known but have enormous chi-squared values and probably do have there's some explanation, there's some reason to believe at least that these drugs administered together do cause heart attack. So they did a wonderful job, but they started off doing something that really didn't work, and we're going to see why it didn't work. And the key issue really is communication. It's the map tasks are generating lots and lots of key value pairs. They all have to be shipped somewhere else to be executed by the reduce tasks. So every key value pair that's generated has to go to another processor, another compute node. And very often, communication is the bottleneck. Okay? And in this case, it definitely was. At any rate, here's what they had. They built records for 3,000 of the 6,000 possible drugs. The other 3,000, I gather, were just not administered enough to have significant data about them. But the record for a drug consisted of the patients that took the drug, when they took it, and subsequent diagnoses. Okay? And on average, the record for a drug was a megabyte long. Remember, this was 20 years worth of data, about 1 million patients involved in this study. And then, as I said, their goal, well, their original goal was to sort of boil the ocean, was to find triples of drugs that caused any side effect whatsoever. But, you know, as often happens, you got to focus on something that you can actually do in a few weeks, and which they did, and it was pairs of drugs, heart attack, very significant question. So they want to, again, what they're going to do is they're going to really apply a chi-square test to the records for each pair of drugs and see whether there is a statistically significant increase in the rate of heart attack among patients that took both compared with those that took only one. Okay, I guess I just said that. Okay, so we have to examine each pair of drugs. So here's what they did. They said the keys are going to be sets of 2 drugs, or ordered lists, technically, since set isn't the type in Java. And the value that each mapper is going to associate as a value will be the record for a drug. Remember, the mapper is only going to get an input of the form, I am drug I, here's my megabyte long record. That's all the mapper gets to see. So what it's going to do is it'll generate all pairs of drugs containing the drug that it is responsible for, and the value it will associate with those keys will be the entire record for the drugs. Okay, so as I said, so the mapper, given the drug I and say its record R sub I, generates all the key value pairs of the form. The key is the set containing I and J, and where J is one of the other drugs besides I, and R sub I, the only record that this mapper gets to see, is the value. So now let's look at this from the point of view of the reducers. The reducer for the set containing I and J is going to get exactly 2 key value pairs. The key, of course, will always be IJ, set I and J, and from one, it'll get the record for RI, from the other, it'll get the record for RJ. And then all it has to do is apply the chi-square test to RI and RJ. Okay, so let's see how this works. Suppose that there are only 3 drugs instead of 3,000. So the mapper for drug 1, well, it'll generate the key 1, 2, 2 being one of the other drugs besides 1, and attach to that as a value the drug 1 data. It does the same thing for the set 1, 3. 3 is another drug besides 1, and again attaches the drug 1 data. The other mappers do something analogous, and then behind the scenes by magic, this all gets sorted by key. Okay. So for example, the reducer for the set 1, 2 gets 2 key value pairs. They both, of course, have the key 1, 2, as it must. One has the drug 1 data, the other has the drug 2 data. And of course, this gets it gets into the key list of values form. That's really not terribly important. Okay, so I guess the day before the midterm progress report was due, they started running this using MapReduce on EC2, Hadoop on EC2. And after 8 hours, they killed the job and came running to me and said, we can't make this. This doesn't really work. Okay, MapReduce really doesn't work on this. Okay, well, let's think about what happened. You have 3,000 drugs. How many key value pairs get generated for each drug? Well, all the sets containing that drug and the 2,999 other drugs. So the 2,999 key value pairs generated by each mapper. See, in my pretty little example, there were 2 key value pairs generated by each mapper because there are only 3 drugs. But this is what you get when you have 3,000 drugs. And then remember, key value pair is essentially a megabyte. Well, you multiply those 3 numbers, you get 9 terabytes. And the interconnection in a typical cluster like EC2 is 1 gigabyte Ethernet. Now that sounds pretty fast, right? If you want to watch a movie, no problem. You know. But the fact is, you had to use 90,000 seconds. That's about a day's worth of network. Now, you have many gigabit Ethernets connecting different processors on different racks and within racks and so on. So it's a little more complicated than that. But of course, you also have other jobs competing with you for use of those. So it's kind of hard to say exactly how long it would take them to finish, but they weren't going to get it done in 24 hours. Okay. So they were right to kill the job. Okay, so at any rate, we talked about this, and again, we focused on the fact that the problem was communication was way too high. Okay. Notice that this is not exactly a big data problem. The 3,000 megabyte files fits in the main memory of your laptop. Okay, that's not where the problem is. Okay, you have to do 4.5 million chi-square tests. That's a lot of computation, but if you have 100-way parallelism or something like that, it's not a big deal. The big deal was the communication was too high. So they came up with a scheme. I'm going to just simplify it, but let's suppose you group the drug into 30 groups of 100 drugs each. Okay, 3,000 drugs. So first, the first group is drugs 1 through 100, and so on. And then I just want to let G of I be the number of the group into which the drug numbered I goes. Okay, now here's what the map function does. First of all, a key is now not a set of 2 drugs, but a set of 2 group numbers. Okay. So there are only actually 435 sets of 2 group numbers. That still lets you do 435-way parallelism. That's a lot. And now the mapper for drug I is going to produce 29 key value pairs. And each key, we're going to set of 2 groups. One of the groups will be the group G of I, the group that the drug I belongs to, and the other member of the key set is is any one of the 29 other group numbers. So you can produce 29 key value pairs. The values, of course, are it's really the record for drug I. You now have to tag it with I so that you know that this is the record for the particular drug I. In the earlier scheme, you didn't have to worry about that because the chi-square test is symmetric. You get two drug records. You don't even care which is which. So the reducer now. Okay, the reducer for the pair of the groups M and N will get, of course, the key will be the set containing M and N. And it will get as a list 200 drug records. The 100 that come from that are in group M, the 100 that are in group N. Now, the job of a reducer is to compare each of the records from group M with each of the records from group N. Okay, so it's going to actually do 10,000 chi-square tests. But each chi-square test just gets run once, right, by one reducer. You do have to worry a little bit about what happens inside a group because that is, there are going to be 29 reducers that get all the members of one group. You don't want to compare inside a group 29 times, so you have to have some scheme to decide who is going to be, which of the 29 reducers is responsible for any particular pair of drugs that are within the same group. It's not really important. Okay, but what is important is if you avoid this redundancy of comparing intra-group drugs 29 times, then each pair of drug records is compared at exactly one reducer. Okay, so the computation doesn't change. It's exactly the same computation that you did in the earlier method that had so much communication. On the other hand, the communication now is 3,000 drugs, 29 key value pairs per drug, so you have to multiply that by 29, and then of course you still have the megabyte per record, so you get 87 gigabytes. That's still a lot of communication, but it's 101, or it's not 1/100th of the communication before. So they were able to get this thing done in a few hours. Now, with that as an example, I want to start thinking about the sort of things like that. Okay, so I want to develop a theory, and it hinges on two things. One is the reducer size. Reducer size is the amount of data that you're willing to let one reducer receive. It's sort of the length of the list of values, or how many values is a reducer allowed to receive. The other is a replication rate. It's the number of key value pairs generated per input. In one case, it was 2,999, then we reduced it to 29, and so on. Now I want to talk about a mapping schema, which in some sense is an abstract representation of a MapReduce algorithm from which we can produce lower bounds, show that certain things, certain problems can't be solved using MapReduce any faster than such and such. Well, what it really is for a given reducer size, the replication rate has to be at least as much. Roughly, the bigger you let your reducers be, the smaller your replication rate can be. Sort of in the extreme, if one reducer can handle all the data, then you just do it as a serial algorithm. The replication rate is 1. Okay. But what the theory really is giving you is a trade-off between reducer size and replication rate. Okay, so let me not talk any more about this. Let me give you the concrete facts. Okay. Okay, so the model for a MapReduce algorithm will be, first of all, have a set of inputs. That's the nature of MapReduce. And then there's a set of outputs. So in the example we've been playing with, there's an output for each pair of drug records. The inputs are, of course, the drug records themselves. And then there's a many relationship that tells for each output what inputs does it depend on. So in our example, that was very simple. And the output representing the set containing I and J, or the pair of drugs I and J, is related to input I and input J, and no other input. Okay, and this is true whether you group the drugs or not. Okay. Okay, so here's the input-output the relationship for a case of 4 drugs. For example, the output for the pair 1-2 is related to drug 1 and drug 2 and not to the others, and so on. So there's a picture of that pattern. This is a more interesting example, perhaps. It's part of the input-output relationship for matrix multiplication. I'm assuming these are n by n matrices. And I'm just showing you one of the n-squared outputs, the output in row I and column J. Now that output depends upon all the inputs in the first matrix, row I, and the second matrix, row J. Now, if you overlay this pattern, n-squared times, for all of the outputs, then you get the entire input-output relationship. If I try to do that, of course, it will be just a big black blur, but I hope you get the idea of what that input-output relationship is. Now, as I said, reducer size, which I always want to represent by a golden Q, again, is the maximum number of inputs that I will allow a reducer to have. That really means it's a bound on the length of the value list associated with the key for that reducer. Now, for example, you might want to say, I'd like the reducer to do its job in main memory. If you're going to do computing chi-square tests, you'd like them all to occur in main memory. Because if you start having to swap to disk, it's going to just take much, much more time. So you might ask yourself, well, how many inputs can a reducer handle and still not have to go to disk? These days, lots and lots of main memory. You still might want to make an artificially low Q in order to force there to be a lot of parallelism. Again, if you make Q too big, you just send the solution seems to be send everything to one reducer and just let it do the serial algorithm, and that's not really what you want. But okay, again, for one of these reasons, you're going to pick a value of Q and say no more input than this to any reducer. Okay, then the other key parameter, again, which I'll denote by blue R, is the replication rate, and that's just the average number of key-value pairs generated from an input, and that is the total communication. Sorry, it's the replication rate is the communication per input. And typically there'll be millions and millions of inputs. The replication rate R will be something like 29 or something like that. Okay, so let's think about the drug interaction problem, but now let's do it in generality. I want to say we'll have G groups. G was 30. Well, the first example, G was 3,000, where each input was its own group, each drug was its own group. Then in the improved algorithm, I had G equals 30. D was 3,000. Then generally, let's just let D be some parameter. Now, we can very easily calculate the reducer size. That is, if there are D drugs divided equally into G groups, then there are D over G drugs per group. And a reducer takes two groups and compares them. So the total number of inputs would be 2D over G. So that's why you see that formula, Q equals 2D over G. Now, what's the replication rate? Well, if you think about it, each input is sent to G minus 1 reducer, so the replication rate is going to be G minus 1. Well, I'm going to call it, say R equals G. I'm assuming G is fairly large, so G and G minus 1 are really the same number. Okay, and so let's just say that R is G. And I claim, well, let's see. We have Q is 2D over G. I said G is R, so Q is 2D over R. And then, since R is really the dependent variable and Q is independent, I'm just going to swap them and get R is 2D over Q. Okay. And this is cool. It says, by picking different numbers of groups, I can, there's this natural trade-off between the reducer size and the replication rate. That is, the larger I allow my reducers to be, the smaller I can make my my replication rate. Okay. Okay. Now, remember, I was describing a particular algorithm. And by the way, it turns out not to be the best algorithm. For the particular, the all pairs problem that we talked about. But what I want to talk about now is how you get a lower bound to show that, in fact, R has to be at least what that algorithm gives. Well, that's actually not quite true, but within a factor of 2, it is true. That is, R has to be at least D over G. And the algorithm I gave you 2D over G. But I'm going to show you a lower bound that R has to be at least D over G. Okay, so now the way I want to think about it is a mapping schema. Okay, well, is for a problem. Remember, a problem is really a relationship between the inputs and the outputs. What inputs does each output depend upon? And Q is a reducer size. And so a mapping schema is really a solution to the problem. First of all, mapping schema assigns inputs to reducers. That is, the problem itself is described by inputs related to outputs. The mapping schema, which is the solution to the problem, describes how inputs are related to reducers. So mapping schema, again, I can take each input is assigned to some set of the reducers, and the first condition is no reducer is assigned to more than Q inputs. Well, that's what reducer size is, right? But the second condition, which is maybe more important, is it says that this mapping schema actually solves the problem. Now, what that means is that for every output, some reducer receives all the inputs that it needs to solve to compute that output. Okay, and if it's sort of necessary and sufficient in that if some reducer gets all the inputs it needs, then since you can write arbitrary code, you can surely figure out how to produce that output from the inputs because the output only depends on those inputs. Okay. Okay, well, the term I want to say the reducer covers the input. Okay, so covers the output. So every output has to be covered by some reducer. That's really the mapping schema condition. Now, in some sense, the existence of mapping schema is a requirement that a mapping schema exists to solve a problem. I see it as what's special about MapReduce algorithms as opposed to just parallel algorithms in general. Let me not, though, go into that in too much detail. Anyway, so let's get the lower bound for the drug interaction problem. Again, I'm going to assume that there are D drugs, and the reducer size and parameter, just it's Q, whatever Q is. Now, I claim that the nature of the input-output relationship says that each drug has to meet each of the other drugs at some reducer. Okay. Now, if I send a particular drug to a reducer, then I can only send Q minus 1 other drugs to the same reducer. So, okay, well, you just do a little math in your head. What that says is that each drug must go to at least D minus 1 over Q minus 1 reducers. Again, because it's got to meet D minus 1 things, can only meet D minus 1 of them per reducer, and therefore it's going to go to at least D minus 1 over Q minus 1. And since, in fact, it must go to an integer number of reducers, that says that R is, in fact, the ceiling of D minus 1 over Q minus 1. Well, again, since D and Q are probably large, what that really says is that R is at least D over Q. And remember, the algorithm I gave you had R equal to or less than 2D over Q. So there's this factor of 2 gap. Now, I want to talk about, actually, a better algorithm that, in fact, that gives you R equals exactly D over Q plus 1, at least for a large, not for every D or Q, but for an infinite number of pairs. So the lower bound is actually the best lower bound that can be achieved. Okay. So let's see. Here's the problem. If you think about it, let's look at it from the point of view of a reducer. It gets 2 groups. Its job is to compare all the guys from one group with an equal number of guys from the other group. So the intra-group pairings, well, it might do those, but most of the time it's not going to have to, because again, there's G minus 1 reducers that get the same group, and so only one of those should be comparing within a group. So as a result, the easy pair to groups algorithm, each reducer only gets to do about half the possible pairs that it could do. Okay, so when you think about it that way, it shouldn't surprise you that, in fact, the problem is the upper bound is a factor of 2 too high. The lower bound is okay. Now, the better algorithm, in fact, busts things up into much smaller groups. And now each reducer is going to get a lot of little groups, and it's going to compare each of them from different groups. There still is a matter of you don't want to redundantly compare guys in the same group, but now the groups are so small that the extra doesn't matter. Okay. Okay, so let's see. Again, I'm going to assume D inputs, and I want to let P be a prime, and I have to assume that P squared divides D. Okay, so maybe D is 900 and P is 3. Okay. Now, I want to divide the inputs into P squared equal sized groups, and each group, of course, will have D over P squared inputs. That's why I want D to be divisible by P squared. And I want to think of the groups as being numbered, sort of arranged in a square. I decided last night that this little grid should help you. The groups, again, are squares arranged in a P by P grid. This is, in this case, P is 5. Each group is numbered sort of by a row and a column. Okay. Now, I'm going to use P times P plus 1, or P squared plus P, reducers, and I'm going to organize them into P plus 1 teams. Each team gets P reducers. And for the first P teams, the members of group ij, well, as it says, is sent to I plus kj, all computed modulo P. Okay. So, in other words, for the, if k is the group number, for k equals 0, j doesn't matter at all. It's just the row number that matters. For k equals 1, then it's I plus j modulo P. For k equals 2, it's I plus 2j modulo P, and so on. And then there's a special team, the last team, which is team P. Group I is sent to the column, just the reducer j. I is ignored. So I don't know if this is helpful or not, but there's such pretty colors I couldn't resist doing this. So this is a picture of team 0. The 5 colors represent the 5 reducers. This is again P equals 5. the 5 colors represent the 5 reducers in team 0, and they just correspond to the rows. Now, in team 1, the 5 reducers correspond to the minor diagonals. Okay, you can sort of see that pattern. For team 2, it's knights moves. Team 3, it's knights moves in the other direction. Team 4, it's the major diagonals. And team 5, it's the columns. Now, what I would like you to have noticed from those pictures that flash by is that for any pair of the 25 groups, they have the same color in exactly one of the teams. Okay. Well, I'll leave the slide so you can check it out later. Anyway, here's an argument as to why it works. So suppose I have inputs in 2 of the groups, say ij and I prime j prime. Again, remember the groups are arranged in this nice square. So if they're in the same group, then obviously they'll go to some reducer in common, so that's not a problem. Now, if their row numbers, j and j prime, are the same, then sorry, it's typo. I didn't mean group P. They share a reducer in team P. Okay. And if J is not J prime, then I claim they'll share a reducer in team K, well, provided this holds. That is, I plus Kj equals I prime plus Kj prime. Oh, I'm sorry, all this arithmetic is done modulo P. Okay. So, now, what I wanted to show you is that there has to be some K for which that's true. Well, just grouping things, I have I minus I prime equals K times J minus J prime. That's just grouping things. And now, I'm assuming that J is not J prime, and therefore J minus J prime has an inverse modulo P. That's the nice thing about primes. Every integer at sub 0 has an inverse modulo P. As a result, that lets me solve for K. There's a unique solution, which is I minus I prime times J minus J prime inverse. Okay, so that's the proof that it works. Okay, now, I'm sort of running out of time here. So I claim it's optimal, at least for those Q and D for which there is a prime whose square divides P, okay, so the replication rate is P plus 1, right? Since every group and therefore every input gets sent to one reducer of each of the P plus 1 teams. The reducer size, well, is D over P, and the argument is this. It says a reducer gets P groups. Each group, remember, is of size D over P squared, because that P squared is the number of groups. And P times D over P squared is D over P. Okay, so that says that P is therefore D over Q, and R I can write as D over Q plus 1. Remember, I'd like it to be R equals D over Q, because that was the sort of the upper bound. But, well, okay, I'm not going to go into this, but what the interesting thing is, as long as, again, as long as this is one of the Q's and D's for which there is this prime P, then the difference between the upper bound, which is D over Q plus 1, and the lower bound without the ceiling, it's less than 1. Okay, and again, I have to assume that Q is less than D, but if Q is equal to D, then we just do it as a serial algorithm. Okay. Now, so the interesting thing then is if the upper bound and lower bound differ by less than 1, and they're both integers, they've got to be the same integer. Okay, so even though there is this little bit of redundancy because you're still doing the intra-group thing, where you have you have many reducers that could do the intragroup things. It looks like there's a little redundancy, but there actually isn't. You actually get an exact match with the lower bound. Okay. Now I just want to close by talking about two different problems. I'll just tell you what results we have. First is the Hamming distance 1 problem. We're given bit strings of length b, and the Hamming distance, of course, is the number of bits in which, or number of positions in which two bit strings differ. So the Hamming distance 1 problem is given as input a collection of strings of length, of bit strings of length b. Find those that differ in exactly 1 bit. Now there's a theorem, I'm not going to go into it, that says the replication rate has to be at least b divided by log base 2q. This is different from what it was with the oil pairs or the drug interaction problem, where it was r is some constant divided by q. Here it's divided by log q. And it turns out that there are the gold line is intended to be the lower bound, and there actually are a number of algorithms that match the lower bound exactly. For example, if q is 2 to the b, that is all possible strings, then I can just send them all to one reducer and have that reducer figure it out somehow. So you get a replication rate of 1. And remember, log base 2 of 2 to the q, 2 to the b rather, is b. So r is b over b or 1. Similarly, with a reducer of size q, or 2 to the first power, you can have one reducer for each pair that are at distance that differ in only 1 bit. There will be b such pairs for each bit string, so the replication rate becomes b. And again, you have the replication rate of b is 2 divided by log base 2 of 2, or which is 1. So it's r and is equal to or greater than b. And then there's some splitting algorithms, and I won't go into that. But basically for any integer replication rate, there is an algorithm that matches this bound. Then there's matrix multiplication. I want to assume multiplication 2 n by n matrices. There's a theorem again, which I won't prove. It's not too hard. That says the replication rate is at least 2n squared over the reducer size q. There is a matching algorithm which you divide the first matrix into bands of size that's actually n over width n over g. There again, side is n. They're g groups, so n over g per group. And the product of these two bands produces that little square of output, and that gives you a matching replication rate of 2n over q. One of the interesting things, which I don't want to go into too much detail, is that if you use a cascade of 2 MapReduce jobs, you get a better result. Basically, you divide the first job divides the 2 input matrices into rectangles, and a reducer takes 2 rectangles, one from each of the matrices, multiplies them together, doesn't give you any outputs, but gives you a contribution to one of the outputs, or some little square of outputs. And then the second job just sums the partial sums. So here's what the first job does. It would say multiply the blue and yellow rectangles, and it would give you a contribution to the green area. Okay, not the answer in the green area, but something which, when summed by the second job, will give you the answer to the green area. Well, it turns out that the one-job method, remember, so the replication rate is 2n squared over q. Where there are 2n squared inputs, so I have to get the total communication, I multiply the replication rate by 2n squared. I get 4n to the fourth, so 4th over q. Now, then I'm not showing you this, but the two-job method, the total communication of the two jobs is 4n cubed over square root of q. Now notice that Q is less, has to be less than n squared, or you really, it just becomes a serial algorithm again. Now, if let's say if Q is n to the 3 halves, then 4n to the 4th over Q is 4 times n to the 5 halves, and 4n cubed over square root of n to the 3 halves is 4 times n to the 9/4, which is less than n to the 5 halves. So there is a significant measurable difference in the 2-job method. It really is better than the 1-job method. Okay, so let me shut up here. Let me just a quick summary. Remember, okay, we're going to represent problems become input-output mappings. The mapping schemas are input to reducer mappings, and that's how we get lower bounds on how much the replication rate is a function of the reducer size. For the drug interaction, they're all pairs. We got rid of an exact match between the upper and lower bounds. For the hanging distance 1, similarly, get an exact match. 1-job matrix multiplication, again, we have also an exact match. And we also showed, or claimed, that 2-job matrix multiplication actually leads to significantly less communication. Okay, and that's it. Okay. Thank you.
Does anybody have any questions?
It seems we do.
So you got to make sure you speak into that mic so the webcasters can hear.
Hi. So I have a question regarding how we actually practically help people solving problems. Let's go back to the drug example. So I calculated the lower bound, the upper bound. That's fine. But then for any particular instance of the problem, what is the optimal solution? In other words, I have the lower bound.
So the noise of people going in and out has made it impossible for me to quite
if I have a very specific problem.
Yeah. Okay. Well, let's say hanging distance 2. Okay.
Yes.
Which is a problem we haven't been able to resolve.
I have
yet.
a specific set of inputs, and I want to solve it. I have the lower bound. I calculate it any way I want. But then, what is the actual, ideal number, optimal number of reducers? Let's say to solve the problem with minimum time.
Okay. Well, okay. This is something we didn't go into, but in all the example problems we've worked out, the number of reducers is the minimum number of reducers that you can use. That is, there's never any advantage of using more reducers and having them each have less than Q inputs.
That's assuming computation is always less costly than communication.
Okay, this is only. Well, I'm sorry. This is just for the trade-off of replication rate against. Again, remember what we have is a trade-off. Okay, the reducer size, in some sense, is a measure of parallelism and computation. The replication rate really is communication per input. You can't control the number of inputs. That's whatever you're given. So it doesn't tell you it doesn't tell you what to make Q and what to make R. Okay, that depends upon the relative cost of computation and versus communication, and that can differ, right? You buy, you run this thing on a blue gene, communication is relatively cheap, but there's always a trade-off, and this isn't really what we're saying. You still have to decide. Convert computation and communication to common units so that you can figure out where on that curve.
Would you say then the next step to practically solve problems like the one facing your students is you have a model of computation, you have a model of communication, and then you solve optimally what is the right partition of the problem in order to minimize.
Yeah, right. So in other words, they could have thought about, okay, what's the exact right number of groups to use in order to to pay the least amount to EC2 to get the job done. I have no idea what that number is. I think they actually used around 10 groups, not 30. But we don't know whether that's optimal. The point is there's going to be some optimum. It didn't seem to make sense, having gotten the answer once, it didn't seem to make sense to run it to see if we could do it more cheaply. Okay, but yeah, you'd have to know something about what the running time of, how much running time do you need for your processors? What does communication actually cost you in terms of dollars paid to Amazon? You maybe have to figure in the fact that you rent processors by the hour, so it's not even a linear function. So to actually optimize it before the fact, not that easy. Okay. What you can do, I think, fairly easily is figure out how big the reducers can be and still run in main memory. Okay, that's an important question, because almost if they can't run in main memory, you're dead. And if it turns out that you can run in main memory with a very large queue, you may say, well, gee, am I getting enough parallelism? So the bottom line is you always want Q to be as large as possible, but no larger than not so large that it either kills your parallelism or forces you to use disk. And that's probably good enough. Okay. But again, if you do something computationally intensive in the reducers, that might not be true. Okay. Okay. Anything? Okay. Thank you.